right here. First off, pH. I don't have this in your notes because this isn't going to be a test question or anything like that. But the reason why it's lowercase p and uppercase h is the uppercase h stands for hydrogen. The lowercase p stands for power. pH is technically the power of hydrogen. Recall last class period. What makes something an acid? Well, to recognize it, it starts with a hydrogen. And that's important because acids give that hydrogen. So when it's the power of hydrogen, it's referring to how much hydrogen ion has been donated. If there's more donation of hydrogen ion, it's a stronger acid. It's got a lower pH. Tricky part with this is bases also use the pH scale, even though technically, again, they're not dealing with the hydrogen ion. Bases are dealing with hydroxide. There's a lot of math that allows us to use this so that we don't get into in Chem 1. So, first off, we are, again, simplifying this for you. But when it comes to Chem 1, we can say 7 is the neutral point. Water is one example of something that's neutral, but there's a lot of things out there that are neutral. Quite frankly, as far as you guys are concerned, if it's not an acid and it's not a base, it is neutral. For example, salt water would be a neutral solution. Gasoline would be a neutral solution. On that pH scale, if you are below 7, you are an acid. If you're above 7, you're a base. Now, typically, the pH scale is advertised as a 0 to 14 scale. However, you can actually go below 0 if you have a high enough molarity of your acid. You can go above 14 if you have a high enough molarity of your base. So 7 is in the middle. 7 is neutral. The further away you get from 7, the more of an acid you are, or the more of a base you are. And sometimes with the number scale for pH, that throws students off a little bit. Because we're accustomed to seeing big numbers meaning more. And that would be true for a base. A base with a pH of 14 is more dangerous than a base of a pH of 10. The opposite is true, though, for acids. If you have an acid of a pH of 0, that is much more dangerous than an acid of a pH of 3. So the further away from 10, which is why the reading guide that you did last time for homework, I asked that you draw kind of like a number scale. The further away from 7, the less that you're like neutral, safe water, and the more dangerous you become. Again, pH technically measures how much acid is in a solution. That's that power of hydrogen part. Remember, hydronium ions is something we talked about last time. When an acid donates a hydrogen in the presence of water, water gains that hydrogen, and it becomes the H3O plus ion. Again, a statement that I just said a little bit before on the last slide. The more acid ions present, the lower the pH. You guys have already actually worked with this year, I believe, acids that are below 0 on the pH scale. I think you used either a 3 molar or a 6 molar hydrochloric acid when you added it to the metal in a single displacement lab and it bubbled out of control. I think you also added a 6 molar hydrochloric acid when you add to the precipitate in that little test tube to create those carbon dioxide bubbles. Once it's an acid of a molarity greater than 1, it's actually below 0 on that scale. Now, you may have had a math class talk about pH with you, just like you may have had a math class talk about earthquakes with you. Earthquakes are measured on something called the Richter scale. Does that ring a bell at all? Acid-base chemistry is measured on a pH scale. They both deal with logarithm. Logarithm is a power of 10 scale. Now again, there's a lot of mathematics that goes into pH, and why we can even measure bases when it comes to pH. There's conversions that we can do. Boy, in AP Chem, we hit a lot of that stuff. For Chem 1, we want you to just to be familiar with this idea of a power of 10 scale. So first off, as you get further away from 7, you are more acidic if you're going lower, or more basic if you're going higher. Secondly, the number value on the pH scale from a 6 to a 5 to a 4, and there's decimal values in between all those, it's not just a whole number thing. It's a power of 10 difference for each of those. So what I'm going to do here is I'm going to switch off this and go to the Smart Notebook, for example. I'm going to show you kind of that timeline of pH a little bit to show you what I mean. But this last point on this slide is going to describe that as well. Now when you have a pH of 2 versus a pH of 4, I mean 4 minus 2 is 2, but the difference in the amount of acid is 10 to the second power. That's what I mean by logarithm, and that's why I know some math classes, I talked to Mr. Aker about this a couple times, about how they will teach pH a little bit. So, if right here is 7, that is neutral water. Again, we could have 6, 5, 4, 3, 2. It could keep on going and going and going. And on the other side, we have 8, 9, 10, 11, 12. And again, it can keep on going and going and going. So I have the pH listed here. A pH of 6. Remember, on this side of that graph, it's acids. A pH of 6 is 10 times more acidic than a pH of 7. Now, some people think, wait a minute, pH of 7 is neutral. That means there's no acid in it, right? Technically, to be a pH of 7 means it's equal parts acid and base. They've neutralized each other. A pH of 5 is 100 times more acidic than that neutral, which means it's 10 times more acidic than this. pH of 4 is 1,000 times more acidic, 10,000, 100,000, so on and so forth. As you get further away from 7, it becomes more and more and more acidic. And technically, water has a little bit of that acid ion in it. It just also has a little bit of that base ion to balance it out. And actually, I know the molarity of that acid ion in water. It's 1 times 10 to the negative 7th power. So 0.00000001. So there's barely any acid in water at all. But that's also the reason for 7 being the middle of the pH scale. Now bases, on the other hand, are above 7. So that means a pH of 8 has 10 times more, remember, of the hydroxide than water. Then 100 times, 1,000 times, so on and so forth. So we want you to be aware of a couple of things with this pH scale. The first one is acids on one side, bases on the other. Secondly, we would like you to be aware of this idea of it's a logarithmic scale. If I asked you a question of how many times more acidic is a pH of 2 versus a pH of 5, well, 5 minus 2 is 3, so 10 to the third power, 10 times 10 times 10, is 1,000. This is 1,000 times more acidic than that guy is. And we can compare it to anything on this scale. So really, those are the main things we want you to be aware of, is just, hey, a pH scale measures how acidic or how basic something is, but then what do those numbers mean? It falls in line with a logarithmic scale. Now, the only other thing that we need to go over today, then, in order to wrap up notes, is something called a chemical indicator. And this was actually mentioned on your reading guide as a characteristic of acids and bases, how they can change colors for an indicator. In about 5 minutes here, we're going to go into the lab. And when we're in the lab, we are going to be looking at acids and bases and water. A lot of these solutions are clear. So how in the world can we tell if it's an acid or a base or neutral? We can add what's called a chemical indicator to it. And what an indicator does is in the presence of certain ions, it will have a different color. And if we have like a little key that tells us, hey, this color means it's an acid of a pH of 3, this color means it's a base of a pH of 10. If we have that little key, we can just add some drops to something that we didn't know what it was, and now we know what we're working with. In the next 2 class periods, we'll be working with chemical indicators in our acid-base chemistry. And there are 2 types of indicators that we'll be working with. Some of them give us an approximate pH, kind of what we talked about today. Is that acid a pH of 5 or is that acid a pH of 3? It'll show us the difference based upon the color. Some of them will simply tell us if we're an acid or base. And that's actually what we're going to be using next time. Because next class, we're not going to be concerned about the pH. We're going to be concerned about when we neutralize the 2. And the second it changes from an acid to a base or an acid to neutral or a base to neutral, we want to know when to stop our adding of chemicals together. Because we want to make it just spot on, it's neutral, it's safe to go down the drain. After all, last class we were writing neutralization reactions. So, my very last slide is going to go over the 2 indicators that we're working with the next 2 class periods. Okay? Actually, if you looked on Schoology, you have 2 slides after this that are dealing with household indicators. If you remember like the hydrangea example from the reading guide, well, there's a lot of things actually in home, like some cabbages and things like that, that you can put in different solutions and they'll change color to show you what they are. Okay, the first indicator that we're working with today is going to be called universal indicator. It's actually in a little dropper bottle. It's already on your lab bench. There's actually a little note card with it that shows you different colors for a different pH value. We are using universal indicator today so we can determine the pH of different solutions. The indicator we're using next time is the most common indicator, I would say, in acid-base chemistry. Because what's most common in acid-base chemistry is to do neutralization reactions. And that indicator is called phenolphthalein. It doesn't tell us different pHs, it just tells us the instance we've neutralized. And that's what we're going to be working on next class period specifically, is neutralizing. I already told you guys that we keep vinegar and baking soda over here in case we have a spill, and that's important to note today. Remember, if we spill a base, we add vinegar to it. Acetic acids in vinegar, it would help neutralize it. If we spill an acid, we put baking soda on it. That's a carbonate type base. It would neutralize it. It would bubble to create carbon dioxide bubbles. But also over here, I have a little dropper bottle of phenolphthalein, because I want to know when things have been neutralized. Because sometimes when we have leftover chemicals at the end of labs, and we're not going to keep it, we need to pour it down the drain. But I can't just pour everything down the drain. If I pour some things that are really potent, it's going to mess with the plumbing in this place. So I have to neutralize. That's why I keep phenolphthalein around. I mean, universal indicator is nice, as you're going to see in a little bit, because they can give you an idea of, hey, is that a 9 for a pH, is that a 10? But to get right to 7, to know the instant it neutralizes, phenolphthalein is typically the indicator of choice. Now, there's a lot of other chemical indicators out there, and actually some of them change at different pH values. And the reason for that goes a little bit beyond what we go over in this class. But our goals with notes today were to familiarize yourself a little bit with the pH scale if you aren't already. 7 neutral, acids are below 7, bases are above 7. The further away you get from 7, the more acidic or the more basic you become, and it's a power of 10 scale. And then lastly, how can we even tell this? Well, there's chemical indicators that can help us with this.